Log on, tune in, find out. Another good idea from Cambridge.
Last talk for today will be given by Oliver Dorn from University of Manchester. The title is Level Set Methods for Inverse Problems.
Okay, thank you very much. I also would like to thank the organizers for the kind invitation to participate in this interesting workshop. At the beginning of this session, it was said that the session is mainly on seismic imaging. Unfortunately, I don't have a talk on seismic imaging. I try to make it as close as possible, so you will see a Helmholtz equation. That's what I can offer you. I hope it's still interesting for you. I think it might be interesting for you because, as you know, medical imaging and seismic imaging, there are many parallels and maybe many analogies, and I will try to point a few out. A short outline. I will start with some general introduction about magic squares. You will see why. I will introduce into the level set technique. I will give two applications in my talk. One is microwave breath screening. This is medical imaging, as I just mentioned. I will also give a geophysical application, namely history matching in reservoir engineering, and I will give some conclusions. Well, before I start, what it is all about, my talk. So we have heard many times already on this workshop that there is some ambiguity in when you solve inverse problems. Most often there is no unique solution. You can write down or you can construct a solution, and you are happy with it because it satisfies the data. Then you show it to a practitioner, and he says it cannot be like this. It has to look completely different. And so what can you do? Here is one example. You see an engraving of Dürer, the magic square. It's very famous. In this corner up here, you see a small square. It's called a magic square. If you look closer to it, you see why it is called a magic square. It's called a magic square because, well, it's a rectangular array of numbers, in fact natural numbers, 16, 3, 2, 13, I hope you can see them. 5 is a little bit turned around, and 10, 11, 8, 9, 6, 7, and so on. It has a remarkable property, namely that you can sum up rows and columns and diagonals and even quadrants and more patterns, each consisting of 4 blocks, and they all sum up to 34. So here is a description of several geometric patterns. If you go through this square, you can just try it with 2 or 3 of them. They all sum up to 34. So if you see this, you think, oh, that's very interesting. That's a remarkable property. Is this the only one, or are there more like this? So in order to answer this question, you might just say, okay, well, working on inverse problems, I just write it down and look for alternative candidates. So let's try it as an inverse problem. Find a square array of m by n numbers such that the sum over all rows, columns, diagonals, and whatever patterns you select being important for you equal pre-specified values. In our case, 34. Okay, well, working on inverse problems, I have to be careful. Inverse problems tend to be ill-posed. So you look at this definition by Hadamard, and you recall, okay, there are different things which can go wrong. And I'm, in this talk, mainly concerned about the second one. Solution might not be unique. And you see immediately why. You write the whole system out. It looks a lot like X-ray tomography or travel time tomography. If you want to compare, you just sum up numbers over lines, for example, or over patterns. You can write it down like a linear system with a matrix, system matrix A, which has zeros and ones. Whatever you want to sum up this a certain component, you put a 1, otherwise you put zeros. You get AX equals B. X is your array written as a vector, and B is a vector of data, which in our case would be just 34 at every position. And then you solve it as you are used to do so, and now you expect, you are very curious, you expect to get all the magic squares which you can hope for. And if you really do this and type it into your computer and solve the problem in the classical way, what you get is this one. So that's everything but a magic square. Well, you can call it a magic square, but it's not what you have expected. But it's a correct answer. And it's an answer, it's a Moore-Penrose generalized inverse solution. Okay, this solution has been constructed to give you exactly that. It's kind of the most boring solution which you can imagine for this problem. So you removed all the structure which you would have been looking for. But it's a correct answer. So what can you do? Yes, you forgot something. You forgot to tell the algorithm that you're not looking for the most boring solution, an unstructured solution. You're looking for a specific solution which has very particular structure. And okay, prior information, that's what you have forgot to put into your algorithm. So in order to select certain solutions, you have to do something. You have to tell your algorithm which solution you are looking for. And well, this is prior information. Some people call it regularization strategies, and that's what my talk is all about. And I will concentrate on deterministic techniques. We have, of course, if you talk about prior information, you always immediately think about statistical techniques, which I will not really touch in my talk here. Possible forms of prior information for this sample toy problem. You can think of many of them. So the first one is the one which, sorry. Okay, so the first one is the one which my MATLAB-based solution gave me, the Moore-Penrose generalized inverse. Then you can think of others. You can, for example, ask for solutions for magic squares where you only have two different values, and also with the same requirement that all the sums which you have defined and specified sum up to 34. And then you can also look at this, in fact, real, as you would say, normal magic square, where all the individual numbers should be natural numbers and different, in particular from 1 to 16. Okay, these are different inverse problems. They are different just because the prior information is different. And they should give you different answers. So the first answer we have seen, it's a least squares Moore-Penrose solution. Of course, as I have written it down, if you change your prior information, you just look for specific patterns which only have two different natural numbers, or in this case natural numbers. Well, there are solutions, of course, and you can construct them very easily. This is one of them, and you can just replace the 13 by 12 and the 4 by 5, and you find others, and you can imagine many more. This is a different solution of your inverse problem with certain structure. It's not the Moore-Penrose inverse. It has structure, and in many applications this might be the preferred solution. Think of material sciences, where each block of your material might, in fact, of your sample might correspond to a certain material. And of course, then you have the magic square. So, how do you construct these different solutions of your problem? That's where the problem occurs, where the difficulty starts. So, first of all, there is not only one magic square. Even though the requirements, the a priori information was or seems to be very restrictive, even for this 4 by 4 case, there are many magic squares here. I have written two more, this one and this one, and so there are many more. And the question is, how do you construct them? So, if you look into the literature, you see that. In fact, I think with 4 by 4 there are hundreds of magic squares already with this just simple 4 by 4 patterns. If you go to higher dimensions, there are thousands or millions of them. So what I want to focus on is, are there any algorithms which can construct you the solution which you're looking for? Not to mention that it might be unique or anything like this. For example, it is known that for these magic squares, well, let's put it this way. For this type of magic squares, if this order is even here, as far as I've read it, there is no algorithm known which can construct these in an automatic way. So if you just ask the question, can I find a matrix squares 16 by 16 in a systematic way, there might be no algorithm for this. Now in my talk, I'm not looking for matrix squares. That would be for the applications I'm mostly interested in, medical imaging or geophysical imaging. Typically, it's not the desired answer. I'm more looking for these type of patterns. But I want to ask the question, are there algorithms which can provide you with these type of solutions for your inverse problem? And that's what I want to focus on. So how can we construct algorithms which give me a certain solution to my inverse problem, which satisfies certain structural a priori information? Why do we need this? Now look just at this simple example here, X-ray tomography. Of course, if you have a nice environment like this one here, a machine highly optimized with rays going through the patient here from all possible directions, you can just do a regular inversion as it is standard nowadays, and you see something which is pixel by pixel value reconstruction. And with your bare eye, you can see structure here. But if you just remove parts of these rays, for example, since you don't want to use such a high doses, or because maybe there are certain implants or metallic implants or pacemaker or whatever, if you don't have the full view, you do not get this nice structured image where your eye can automatically identify structure even though it hasn't been imposed on the image a priori. So what can you do then? Then you can try to enforce structure. And well, that's basically what I want to focus on. How can you enforce structure? It's a little bit slow. Okay, sorry for that. How can you enforce structure? So I want to focus on the level set technique, which is a technique designed to give you structure, very specific structure, namely interfaces. And it has been introduced first by Fadil Santosa, who is here on this workshop, in 1996, and since then has stimulated lots of research on this. And the basic idea is, structure, I define it in my research here by interfaces. You want to identify certain regions in the domain, and which means interfaces or boundaries of regions. And the level set technique is just a technique which implicitly describes interfaces or regions. And if you want to evolve an interface or a region when solving an inverse problem, you can do so by instead evolving the level set function. As you can see here, the zero level set of this higher dimensional function coincides with the boundary of your region which you want to evolve or find. Now, if you just add or subtract parts to this higher dimensional function, then implicitly the zero level set, the location where this higher dimensional function crosses the zero plane, moves back and forth, and this way you have an implicit evolution of this region here. And the nice thing of this implicit form is that you have automatic description of topological changes. So going from here to here, for example, you don't have to reparameterize or anything like this. Okay, microwave imaging. That's one of the applications, one of the two which I want to focus on. Here you see basically a typical experiment which I would consider in this application. If you compare the seismics, of course, you see immediately that the wavelength of the waves I'm interested in here is much larger compared to the objects, which you see in a minute, compared to seismic imaging. Seismic imaging has very small wavelength compared to the objects. Here we have wavelengths which are comparable to the size of the objects. What you register is at the boundary the amplitude and phase of the arriving waves for a few frequencies. and then we want to reconstruct these different objects. And now coming back to this question, which reconstruction do you really want? Here are different reconstruction of the same object using the same data set. Here you see a pixel-based reconstruction. And you see in a minute, this is the correct one. This is the correct object which I put into, which I use for creating data. And here you see shape evolutions created by this level set technique, using level set technique. Now if I ask you which reconstruction do you really prefer, this one seems to be much faster. Well, it's a little bit artificial because I have cut it down, but it is in fact faster. And see, those two, they resemble more in the end, if they really converge, when they converge, they resemble more the correct object. So you might say, okay, no, I don't care. This looks already like what I want to, what I'm looking for. I can extract all the information which I need from this fast, quick reconstruction. That's fine with me. Okay, that's good. But there are applications where you really are interested in details, for example, of the boundary. For example, you want to know certain features at this place here. Now, this pixel-based reconstruction will not give you this information. Those might give you this. So the question is, what do you really want to do finally with your reconstructions? And so I want to show you one example, microwave medical imaging, where this becomes relevant. It is joint work with my colleagues from Universidad Carlos III, Madrid. And the motivation is breast cancer detection. So you might know that for breast cancer detection, mammography is a standard tool. But it's not perfect, it's not optimal. You use X-rays for finding contrasts between healthy and malignant tissue, but it's a very small contrast, so you have many false positives and false negatives. Due to this reason, research is going on to check whether there are other modalities which you can use instead to identify more accurately malignant tumors. And microwaves is one of these modalities which has been discussed recently. Now I don't want to go too much into the details whether it will work in the end or not. So this is X-ray tomography, this is a mammogram. You see here is a healthy tissue, yes, a healthy breast, and here is a cancerous breast. A specialist, a physician can really see the difference here. And the question is, can you do it with imaging? So I want to use microwaves for this. And the setup is more or less as you have seen it in the small cartoon at the beginning. You put microwave antennas around the breast, you irradiate the breast, you take the data and you want to reconstruct. And the model is, that's what I mentioned at the beginning, it's kind of similar to seismic imaging, even though the relation between wavelengths and the size of the object is of course different here. So we are using in 2D the two-dimensional Helmholtz equation, and in 3D it would be Maxwell's equations. Of course, not an elastic equation, but Maxwell's equations. In 2D it is a Helmholtz equation. And we are looking for, sorry for that, we are looking for the kappa of x wave number, which contains the permittivity and the conductivity which are characteristic for benign or malignant tissue. What we are looking for is a small tumor embedded in typical breast tissue. You see here typical breast cross sections built from MRI images. You see a matching liquid surrounding the breast. You see skin, this is a blau circle here. Then in the interior you have fatty tissue which is white, and fibroglandular tissue which is here on the screen blue, or here more green. And you see two different typical patterns for breast tissue. So of course different patients have different structures depending on the age and other parameters. And there are in total 3 different prototypes. And here to the right you see a histogram of the interior permittivity values of the breast. So I'm not discussing in details the dispersion law which I'm using here. So I'm using some dispersion relations. In the end, it is just one parameter, one real valued function which I'm looking for here, a static permittivity. And you see here the graph of this. You see that there are, here is a histogram of values in the interior, not counting skin and not counting a possible tumor. And you see two accumulations which correspond to fatty and fibroglandular tissue. They are not sharp, which means there are variations in fatty tissue. There are also variations in fibroglandular tissue. But you see there are accumulations, and it is justified to treat this in the framework of shape reconstruction. Here you see the same thing with this structure. You see a slightly different histogram, but still the main assumptions hold. Now, applying the level set technique to this more complicated example, of course, it's not just two different regions. So you have to do something more complicated, more complex. What we are doing is using something like a color level set technique. And maybe I show this to you. So I showed you the level set idea in principle for two different regions. So you have, for example, one level set function which looks like this. And this defines you two regions. For example, you could say I identify fat and skin by one level set function. Now you have more tissue types. So what you can do is just take another level set function and superpose this and look at the sign of both of them. And then you could say, okay, I have defined new regions now. The second level set function might be responsible for identifying a tumor. And then, okay, in principle, you could now say, okay, then I'm left with one more region, and I just say this is fibroglandular tissue. Then I have 4 regions, 4 tissue types, and I'm done. This is done in many applications of color level set in image processing. Here it wouldn't work because you wouldn't have an interface between fat and fibroglandular tissue. So what you actually do is you define one more level set function. Okay, now it's getting a little bit messy. But now you say, okay, I identify skin in these regions where I have where my first level set function, which I have defined first, becomes negative. And I have defined already 2 more. I have 2 other more regions here, which I have to, where I can put in new tissue types. I say, okay, fibroglandular tissue is my new level set function, the third one. It stands for fibroglandular tissue. There's one more region here, which I can put some material property to. And in fact, I use 2 more, just for the fact that 2 more can, in fact, grow into fibroglandular tissue. You could put here fibroglandular tissue, which would inhibit the tumor growth into fibroglandular tissue. So you can control somehow, when you construct these level sets, what is going on physiological when a tumor grows into fibroglandular tissue or fatty tissue. Now, if you do this in this specific case, you end up with regions of tumor and fibroglandular tissue and skin, which have joint interfaces. All of them have joint interfaces. This gives you the possibility to define an evolution. If you do this, so you can write it down with mathematics, you can define a coast functional now for the level set functions, incorporating level set functions. You let them evolve. You define evolution laws for the level set function. And for the interior profiles also you keep them active. Then you can look for descent directions. This is all standard. I don't want to go into the details. You can, it's kind of standard calculation looking for descent directions. I just want to show you how it works. Here is an example where you have the breast, and an embedded tumor. Here is a typical pixel-based reconstruction, and here would be a level set reconstruction using this technique of the multi-level set. And here is a cross-section. I want to show you so here the green one is a pixel-based, I think the red one is a correct tumor, and the blue one is a level set reconstruction. And I want to show you the evolution. So first we start with the pixel-based reconstruction, just ignoring two of the level set functions. We only have the skin one. Then we extract a first guess for the fibroglandular region and the fat. And then we add finally the third level set function, which evolves. Now 3 level set functions, and in theory 3 profiles in each region are evolving and finally converging to a very good estimation of the tumor. And now we are looking for the right contrast, which is a final search for the contrast, which I don't explain in detail here. Here is another example where you see the comparison, the correct model, the pixel-based reconstruction where you don't have structure. Here you impose structure by our model. And you see the cross-section of the final reconstruction, and you might want to see here a little bit of the evolution. It is an evolution which is sophisticated and complex, since the model is complex. So you have to do something as well with the evolution. The coast is going down, and it reflects the evolution and the complexity of the model. I don't want to go too much into details here. Instead, let me just go quickly to the next example, which might be of interest to you as well. This is history matching. I have just 3 more slides on this. In the history matching problem, you have a similar situation where you have data which is which most of you probably know, coming from the seismic community. You want to look for permeability in a reservoir. You have injectors here. These are the circles here. And you have crosses, which are the producers. Here you have 4 5-spot patterns. You have a porous medium. You inject water, and you want to extract oil. You have the history of the data, so of the water outflux, and you want to find the profile of the permeability. And you can just apply the same technique to this one, just changing formulas and equations. Here you have a two-phase flow equation, a simplified black oil model. You are looking for permeability here. If the real profile is smooth, the reconstruction gives you a very good approximation to this, or reconstruction with standard techniques. If the real profile is non-smooth, has interfaces, standard techniques typically give you still a smooth reconstruction, and you might struggle to get out of this what you really are looking for. Here is another example. You have this is meandering river or whatever it might be. The pixel-based reconstruction gives you something which you could interpret it being something like this, but it's not really satisfactory. I want to show you now just what the level set reconstruction gives you here. Here's the evolution. Here's, for comparison, the pixel-based reconstruction as we got it. Here is the real profile. For example, a meandering river down there, shale and sand profile, for example. An initial guess. Here's the final reconstruction, which this should converge to, and here you see the coast evolving. The data are just the water production rate in these 9 boreholes which you have seen there. Now again, here both have more or less the same final coast, the smooth reconstruction and the structured one. You have to decide which one you like more. So I cannot really say one is better than the other, but maybe a geophysicist might tell you I prefer this one compared to this, or the other way around. Okay. Oops, sorry. Conclusions. So as I started out, inverse problems have typically more than one solution. So in many applications, you don't have the luxury of really being able to claim in the end, I minimize my cost functional, I found the solution. So depending on the prime formation and other constraints, you might come up with different solutions. And depending on the application, one might be preferred to the other. However, there is one problem, namely some solutions you find easier than others. So there is a need for certain algorithms which gives you certain types of solutions. And we have seen many algorithms here and probably in this workshop, and most of them give you kind of different types of solutions. Now the level set technique is, well, one more algorithm which is tailored to give you a solution with structure, with interfaces. And there are many applications out there where this gives you really an advantage. Being able to find a solution which satisfies your final, your cost or your data, incorporating interfaces. And that's basically the sense of what I wanted to talk about. So thanks a lot for your attention.
Thank you. Now we have time for questions. Please.
Coming back to your example of the magic squares and priors, if you consider white noise and you want to know the prior for white noise, you have a posterior distribution function for that. And you can choose to maximize it to find the most likely white noise image. And you will find that it's all equal to 0, so it doesn't look like white noise at all. So you have to sample that instead of maximizing it. Could it be that we should change our framework or change our viewpoint and actually sample probability distribution functions in settings like this? For instance, for the magic squares, you could imagine sampling from the set of magic squares rather than doing a pseudo-inverse.
But this goes into the direction moving more to statistical techniques, right? Of course, I totally agree. This might be a really good way to handle these techniques. And in fact, there are strategies, statistical strategies, which look for images like those. There are models like a Potts Gauss-Markov model, which are aiming on getting these kind of reconstructions on a statistical basis. Yes, I suppose they are computationally more expensive. So I'm just limiting myself here to get just one solution. This already takes a while, takes some time. If you have the luxury to put a statistics on top of it, you might then use Bayesian techniques. Or maybe this ensemble Kalman filter, which as we mentioned, might be a good solution here then as well. Yes.
You used the word prior in your discussion, but it's just as much about parameterization. And sometimes the distinguish between how you parameterize your model and what probabilistic priors you put on. Very often the first bit is the hard bit. I mean, how many different level sets should you put in, which is more of a parameterization problem than a model choice problem than actually a prior problem. And I think often the model choice problem is much harder than, than adding probabilities later on.
Are you able to calculate the Hessian at the optimum, and that will give you some idea of how reliable the retrieval is?
Of which, in which example here?
In
any one of
example.
them.
So you find
we didn't really try.
At the minimum,
we didn't really try. No. This might be a way to identify, but I mean, in the end, I'm not sure whether this really would give you the answer which one of the solutions would be the preferred one.
Well, if no, it wouldn't do that because that's to do with the prior, but it would if the client says they prefer one of them. If you told them what the second derivatives were, that's actually giving you an estimate of the covariance matrix. If you are lucky, and you very often are, that you've got a monomodal posterior density, because your method is equivalent to a statistical method.
Interesting point. I do not know. Could be.
And it would add a lot of value to the answers, which are already superb.
Yeah. Thank you, Sayed.
Okay, thanks again.